In this video, we will do a mean value theorem example, or MVT. So the example says, suppose f of 3 equals 1, and f prime of x is greater than or equal to -4, and less than or equal to 7 for all x. What is the range of possible values of f of 6? So that means I want to know what's the smallest f of 6 can be, and what's the biggest f of 6 can be. So I can figure out all possible values of that. All right, so I'm going to try to apply mean value theorem for this. To be able to apply it, we need to check the conditions for MVT first. Check the conditions for MVT. So that's the continuity on a closed interval, and it's got to be differentiable on the open interval. All right. So since it tells me something about the derivative, it tells me f prime of x is between, I'm just going to write BTWN to abbreviate between. It's between -4 and 7. This implies that it exists. Our derivative exists. It's just some number between -4 and 7. It exists for all x. So, in other words, that is to say that f is differentiable. F is differentiable. Differentiable means the derivative exists. Okay, it's differentiable everywhere, because this is true for all x. Differentiable everywhere. And we've seen before that if a function is differentiable, then it's continuous. So this implies f is continuous everywhere. F is continuous everywhere. So that means our function is going to be continuous on any closed interval we want to use, and differentiable on any open interval that we want to use. Okay, so we can definitely apply mean value theorem. So let's apply MVT for the appropriate interval. For an appropriate interval. So in this question, because one of the pieces of info is that f of 3 equals 1, and I want to know about what's going on in f of 6, we're going to apply it to the interval from 3 to 6. All right, so this appropriate interval is going to be the interval from 3 to 6. All right, so by MVT, by the mean value theorem, by MVT, it tells me that there is a number c in the open interval from 3 to 6. It's got to be somewhere between 3 and 6, such that, and now I write the conclusion of mean value theorem, and that's that f prime of c, the derivative at c, needs to be equal to that slope of the secant line connecting the point where 3 is and where 6 is. So the slope of the secant line I write as f of 6 minus f of 3 over 6 minus 3. Change in y values on top over the change in x values on the bottom. Okay, but I know what f of 3 is in the problem. It tells me that's 1, so let's substitute that in. I'll get f of 6 minus 1 on the top, and then 6 minus 3 is 3 on the bottom. Alrighty, we know something about what the derivative is always in between. We know f prime of x is always in between -4 and 7. It could be equal to both of them. That was given to us. So this implies that -4 is less than or equal to, I'm going to leave a space, is less than or equal to 7. And f prime of c is a derivative. It's a derivative at a particular point. So that derivative should also be between -4 and 7. So I should be able to plug in f of 6 minus 1 over 3 in here. All right. And now let's simplify this. Let's rearrange this so I can get f of 6 by itself. So I'm going to multiply everything by 3. So I'm going to multiply by 3. That'll give me -12 over here is less than or equal to f of 6 minus 1 is less than or equal to 21. So I don't need to flip inequalities because I was multiplying by a positive number. And now I will add 1 to everything. So plus 1 to get rid of that -1. So I get -11 is less than or equal to f of 6 is less than or equal to, adding 1 to this, I get 22. And now I have it. I have my range of values that f of 6 can take on. So I'm going to box this. The smallest it can be is negative 11. The biggest it could be is 22. And that's my answer. So I was able to get it with mean value theorem. So the method that we applied, I don't think gives us a great geometric intuition for why this is the case. Like, why is the smallest f of 6 can be negative 11? Why is the biggest it could be is 22? So I also want to draw a picture to just confirm that this seems reasonable. Okay, so this picture is not going to be a proof or anything. It's just a supplement for what we did, but I think it's going to be very helpful just to visualize what's going on. All right, so let me draw some axes. And I'll label 3 on the x-axis, and I'll label 6. I'm going to try to spread it out a little bit. And the problem told me that when x is 3, the y value is 1. So I'm going to label that. All right. And the question gives me information about the derivative. It says the biggest the derivative could be is 7. So what that means is if I go to the picture, starting at this point where x is 3 and y is 1, the biggest my slope could be is 7. So I'm just going to draw a dashed line that has a slope of 7. Okay, maybe let me not make it that steep so it's not going to go so high. Okay, so a dashed line with a slope of 7. Let's say something like this. So let's say this is the line of biggest slope. Biggest slope equals 7. I'm going to put a little thought bubble around this. And then similarly, the question told me what the smallest derivative could be. It says it was negative 4. So I'm going to draw a line with a slope of negative 4. Okay, so I'll make that one a little bit flatter. Okay, so this is the smallest slope line. The smallest slope is negative 4. Okay, so if the slope was just 7 the whole way, if the derivative was 7 the whole way, I would just travel along this orange line. And if the slope was negative 4 the whole way, I would travel along that purple line. All right, and I want to know, well, when we get to x equals 6, what's the highest up my point could be, or what's the lowest my point could be? Okay, well, I'm going to draw a little guiding point there. So the highest up I could be by 6, by x equals 6, is up here at the top of this biggest slope line. And the lowest I could be is down here at the bottom of the smallest slope line. So let's figure out, how high up and low I have to go to reach those points. So this is where slope is going to come in. So from 3 to 6, that distance is 3. And if I use my slope formula, so slope as rise over run, or change in y over change in x, if I use it on the biggest slope would be 7. And this rise, let's say I want to know what this rise is. I can just put a question mark there. And then the run was 3. And if I rearrange this, I get that question mark has to be 21. So this is going to be a rise of 21. If I go up 21 from 1, I'm at 22. And that is the biggest number I was getting here. All right, so if I do the same thing with the other line, that slope is negative 4. I would get that's going to be equal to the rise, I'll put a question mark, over the run is still 3. Okay, and if I rearrange this, that question mark is going to be negative 12. So if I go down 12 units, let me just put a 12 here. So I can write it as a length, that's why I'm writing it as a positive number. If I go down 12 units from the 1, I end up at negative 11. And that's the smallest my y value could be. So I want to reiterate again that this picture is not a rigorous proof by any means. It's just an aid to help me visualize what's going on. If I really want to give a rigorous argument to this, which I do absolutely want to be able to give, I need to do it like this with the mean value theorem.